Previously, we have been able to give a closed form expression for zeta of 2k whenever k is a positive integer by making use of Bernoulli numbers whose generating function we found to be x over e to the power of x minus 1. And we were led to this generating function by a hunch that probably zeta of 2k can be evaluated recursively from zeta of 2, zeta of 4, all the way through zeta of 2k minus 2. And in this video, we are going to actually find this recurrence relation for zeta of 2k. And first of all, we are going to need to find a power series for the cotangent for x times the cotangent of x. And to do this, we are going to rewrite this power series for x over e to the x minus 1 in terms of zeta of k, because we can express the Bernoulli numbers in terms of zeta of 2k. And when we do this, this is the expression that we obtain. And we can now actually express a cotangent of x in terms of the exponential function by making use of Euler's formulae. And we are going to have I in the exponent, but we can easily get rid of it by considering ix times the cotangent of ix. And then we can do some further manipulations to eventually find that the cotangent of x has the following expansion. And so I briefly went through the power series for xcot x because we have already seen it in a previous video. But now I am going to claim that this is the recurrence formula for zeta of 2k plus 2 when k is greater than or equal to 1. And to prove this claim, we are going to have to make use of this expansion of the cotangent function and also some other properties of the cotangent function to obtain a differential equation. So we remember, first of all, that by the Pythagorean theorem, the cosecant squared of x is equal to 1 plus the cotangent squared of x. But also we have that the derivative of cot x is minus cosec squared of x, which means that we have the following differential equation for cotangent of x, which is minus d cot x dx equals 1 plus cot squared x. When we use the series expansion we have just found for cotangent of x in terms of zeta of 2k, we find the following series for d cot x by dx. And when we replace this in this differential equation, and also we replace the series for cot of x on the right, we are going to have these two equality of series. And when we simplify a bit, sending this bit here over to the left and so on, we can simplify our expression to the following, and we see that we have to square an infinite series. And that is no trouble to deal with. We can form the Cauchy product. And when we perform this on this series and we simplify, this expression over here will be turned into this expression here, in which we can equate coefficients. And when we equate coefficients, we find the following two expressions. So when we equate constant terms, we find that zeta of 2 equals pi squared over 6, and we obtain the following recursion for zeta of 2k plus 2. And we can rewrite these two as zeta of 2 equals pi squared over 6, and we also obtain the recurrence relation that we claimed earlier. So let us give two examples of using the recurrence relation. So when we put k equals 1, we are able to evaluate zeta of 4 in terms of zeta of 2 only to find that zeta of 4 equals pi over 4 over 90. And when we put k equals 2, we are able to evaluate zeta of 6 in terms of zeta of 2 and zeta of 4 to find that zeta of 6 equals pi to the power of 6 over 945. So very well. Now we must only make one remark, which is that we can turn this recurrence relation for zeta of 2k into a recurrence relation for Bernoulli numbers, just because of this connection between zeta of 2k and the Bernoulli numbers. And I am going to leave it as an exercise, so a very easy exercise to show that this recurrence in terms of zeta of 2k becomes this recurrence in terms of the Bernoulli numbers when we make use of this relation. So this relation is actually quite useful to calculate the first few Bernoulli numbers, as you can check for yourself. So in the next video, we are going to talk more about the power series expansion of xcot x, and also discuss power series expansion of tan x and x cosec of x and the secant of x.